So, good evening to all. Welcome to week 10 discussion of electrical machines 2 course. Uh, Today we'll be discussing a different concept in electrical machines 2. Till now we were mostly concentrated on transformers and three-phase induction machines, and specifically in three-phase induction machines we were discussing um, the different conditions in three-phase induction motor. Those are what are the starting methods of it, what are the speed control methods, torque, speed characteristics, everything we were discussing. How we can derive the torque developed in the machine and current flowing through the rotor circuit. All these derivations we have been looking. So today we'll be discussing a different branch of electrical machines too. Of course, it's a family of induction machines, but with a different um, theme. It is a single phase induction machine. We were totally concentrated on three phase machines because three phase is the commonly available supply, and to run the industries and all we need three phase supplies, and for that application we were using the three phase induction motion that machines, and that's commonly used and mostly used. But there exist the single phase induction machines as well, but somehow they are not popular because a stable three phase supply is what uh, best available and standard were being set in our country, so that three phase induction machines are very well known, and entire behavior characteristics everything is being known to us. Coming to single phase, it's not that mostly used anywhere, but in fans and all we do see that, but the applications are very less, such that we not don't concentrate on single phase induction machines that that deep. Now today we'll be discussing how actually the single phase induction motor works, and how does the torque developed in that induction motor, or the torque equations, and how do we look at it as a whole, that we'll be discussing today. So constructionally, if you see, it also has a stator and rotor, but it's just only one phase. There is no R, Y, B. Only one phase will be there. And constructionally, stator, there will be winding on it, which is single phase, of course. And a rotor in general, it's a cage rotor. Now let's start with our discussion for today. So we'll be discussing the concepts on single phase induction motor. Now, yeah, as I said, stator and rotor will be there. Stator will be having this single phase winding on it, wound on it, and rotor in general is a cage rotor. Now, if we draw this, we can see this winding like this, stator winding, and here we have a rotor, which is a cage one, and we call it as the M, which is called main winding. Okay, there are no RYB, only one winding, and there is the main winding, which is a single phase winding. Now, if we connect a single phase supply source to this particular winding M, what will happen? So that's a point of interest to us today. How this induction motor works in a single phase operation, and we know that there is a main winding for stator, and if I connect a single phase source to this particular winding, here I'm connecting a source. Yeah, this is source is connected. Now, how will this machine behaves? So, will motor run? Will the current will pass through the rotor, because that's what rotating magnetic field is. Whenever you pass a alternating current through a winding, flux will induce, and EMF will be induced, and flux will be time varying, so that you will get a rotating magnetic field. We saw those concepts before. Now, will that the same happen here? Will the motor run, or will the current rotor current pass? That's the question. Now, when see, this is analogous. If you want to look at this particular winding and also this rotor in a machine's perspective, let's say you have a machine like this. Okay, and we have a slot here, we have a slot here, and we have machine like this. And the winding, I have inserted this single phase winding, whatever it is on the stator. This is how we wind. Like it will go like this. It will go like this, and it will overhang, and this will come back like this. So this is how it will be. So entirely one. If you want to see it as a single line winding, so this is the stator. This is how it would be. This is M. This is the main winding. Now, when single phase source is connected to this particular winding M, definitely a sinusoidal current will flow through it, because we are giving a alternating supply, and sinusoidal current will flow through it. Now, this particular current will create certain field. Oh, once again, here. Okay. So this current will create a field. The nature of this particular field is what? How will a alternating current given to a winding at the flux being produced? How will be the nature of the flux? This field. We discussed this already in previous week. I think fourth or fifth week. Like how does a flux or a field nature would be when a single phase alternating current flows through that particular winding. We even gave a name for that particular wave. You can refer to week 5 discussion. You can easily relate to it. So it is. So let me just draw it. Maybe then you can remember. So if there is winding like this, and then I have connected a alternating supply to it, and a sinusoidal current will flow through this current. So current is flowing. Whenever current will flow, you know what happens. Let's say it is flowing like this, and so in some direction. So if it is right hand thumb rule, if it's going like this, the flux will come in this way. Flux is generated, and for different magnitudes of M, like the different magnitudes of current, you will get different flux field distributions. If this time it's the magnitude of current, let's say it is a sinusoidal current you got. Now, for different magnitudes of current, you will get different magnitudes of your field. This is what we have discussed. The exact figure we have drawn in week 5 discussion. You can refer to it for more details. Now, whenever a person or observer standing at the point P, and at this particular time instant is observing the different magnitudes of field that's being witnessed by him. So at this instant, it has this height, this is the magnitude, and this is the magnitude, and after some time he's seeing some negative peaks and negative maximum peak and negative positive peak and positive maximum peak. So between this negative peak and positive peak, the magnitude of current is being changing, and he's not observing the sinusoidal behavior, but just a rise and fall of the amplitudes of this current. So the name we have given, it's a pulsating, right? It's a pulsating wave. So this is the name we have given to it. So I think we are given standing pulsating wave, if I'm not wrong. Standing at a point P, and if you can see the pulsating wave that is oscillating between positive and negative peaks, and the magnitude which depends on the magnitude of current that is flowing through the winding. Now, will there be a rotor current? So this is what we are flowing through the stator. So, there will be a rotor current? So the answer to that question is yes, there will be a rotor current. Now, because if we consider a single turn, like through which we are flowing a time varying flux. Time varying flux is in passing. So it will definitely induce the voltage. It will definitely induce the voltage, right? So because of the Lenz law, there is a time varying flux is there. So it is changing with respect to time, d phi by dt, and there will be a induced voltage E will be induced. E is equals to minus and d phi by dt, that we know that. Now, Similarly, if you take any turn or coil, all these turns and coils will be carrying some current. So it will just behaves as a transformer where the secondary is short circuited. It's just like the primary is where we are flowing the current, and secondary we will induce a voltage. And now, as far as this rotor distribution is concerned, like how will be this rotor current distribution? So it will also be uh, similar to the Garning law, which we discussed in the transformers discussion, that is Lenz's law. At any time, you can see this Lenz's law being followed, and in this, here also it's the Garning equation is a Lenz's law only. Now it will try to oppose the stator field, as we know, because if you see the kinds of flux fields being produced, here I am drawing. This is the stator winding, and this is the rotor winding, and we have, let's say, this is the axis, and we have some slots. Okay, now I am a sinusoidal current, alternating current is flowing through this winding, and let's say current is flowing like this downwards, and I have produced a field in this direction, flux, that is the stator field that I have produced. And let's say your stator rotor coils are having this kind of polarity, crosses and dots in the bottom. Now if you see like this, and the bottom one is into the paper and bottom one is outside, so if you use the right hand rule, the flux generated, the flux produced by the rotor would be in this direction, this direction. So now if you see the directions of it, that is stator field, and this is the direction of rotor field. So will it, yeah, of course, because of the Lenz's law, we know that the field of both stator and rotor would be opposite. Yeah, they will opposite. The cause and effect, they oppose each other. Now, will these two forces will flux fields will produce the torque? So that's the ultimate question, right? So I have a single phase induction machine, and I'm passing a sinusoidal current through it, and I'm now want to see if my machine will rotate or not. Ultimately, what you need your motor to rotate. Will it rotate or not? Now here we have two fields, stator field and rotor field, and the current is passing through the winding, and your rotor is also has some its own field. Now the torque, the force required to rotate this particular motor, will the torque be produced or not? So the simple answer will be no, because if you see these two fields here, stator field and rotor field, even though they are opposing to each other, they are having along you mean they are the same axis, their plane is same, the angle difference between both are same, their phase is same, so they're acting along the same direction. So what I'm concluding now is, till the discussion we had till now, your machine will not rotate. That's what I observed. Your machine will not rotate. That is, if you have a single phase induction machine having single winding on the stator, it has no starting torque, because to require torque you need to have two forces acting on the body, and the angular difference between them should not be 0 degree or 90 degree. They should not be in the core phase. There should be some angular difference between those two. Now whatever I observed is that I have passed the current through the winding, and some field is generated, induced, EMF is induced. Now I am seeing as a whole, these two fields, stator field and rotor field, are acting along the same direction. So that's definitely not a criteria to have a torque developed. So I'm now concluding this. Your single phase induction machine having single winding on stator will not rotate because it has no starting torque. You cannot have a starting torque because of the orientation of these two fields, and because there is no starting torque, your machine won't rotate. So that's the conclusion. The first observation I am concluding here is machine will not rotate, and single phase induction motor having single winding on stator has no starting torque. So yeah, these are the two conclusions I am drawing from our discussion till now. See, I have a single phase induction motor and I have given a alternating supply to my stator winding, that's the main winding, and I'm seeing whether my rotor will rotate or not. There will be enough torque produced for my rotor to rotate. So the answer is definitely the fields will be produced, because whenever you pass an alternating current through a winding, flux will be induced, and the flux which is induced will be time varying in nature. Because of the time varying nature, your EMF will be induced. Now the question is, will your motor rotate? No, your machine will not rotate, because of both forces, stator field and rotor field, are having the same, are acting along the same reference, so that the torque will not be produced. So what I'm concluding is, your machine will not rotate, and your single phase induction machine having single winding on stator, there will not be any starting torque for your motor to rotate. That's my conclusion. Now what will be the remedy for this? How can I make my rotor rotate? So you can do that if by some mechanism, maybe you take a prime mover, and if you rotate the rotor, initially you will give the starting torque to, by surprise you can see that you will find the machine will slowly pick up its speed. I mean, in whatever direction you have rotated the motor initially, whether clockwise or anti-clockwise, you have given some external movement, and depending on which direction you have given the external rotation, for your surprise you will see your motor will start picking up speed and it will rotate. So that's the remedy for this. That's the way you can achieve some starting torque to your particular motor. So conclusion would be, however, whatever like you are trying to rotate single phase induction machine, if I able to give a starting torque to it, then no need to give the running torque. It has its own running torque. The only problem was starting the motor. Now, if by some mechanism, if you could give some starting torque to that machine, then there is no question of having a rotating torque, because you have seen, like, rotating torque will be there anyhow. So once you give it some starting torque, it will pick up its speed and it will slowly have a running torque. So therefore, to make this particular induction machine work, we need to incorporate a starting torque. So we have to give our starting torque to machine. Now, how we are going to achieve this? So we can achieve this by placing another coil on the stator. So that will be your extra coil, or you can say auxiliary coil. So main winding is only one. That is the main winding on the stator. Now, if we can go for another extra winding on your machine, which will be working as a your auxiliary winding, then there are chances that you can able to rotate your motor. So now your machine is capable of picking up speed, that we have seen. That means it has some running torque. Now we will disconnect that, like once it achieves the speed, and once it builds up the speed, you will remove that auxiliary winding coil from the supply, because the purpose of auxiliary coil is only to give a starting torque. Now that we have achieved it in the motion and the motor picked up its rotating torque, so there is no need to that auxiliary winding no more. The whole intention was to raise the give the starting torque of the machine. Now let's see how it works. Let's consider, one second. Okay. So let's consider two-phase induction machine because we are trying to incorporate secondary extra winding to make it have some starting torque. Now let's see how it works. Now instead of single phase machine, I would ask you to imagine a two-phase machine. Uh, so don't worry about how why are we discussing two-phase, because uh, whatever we are expecting is a discussion on single phase. Then why are we going for a two-phase? So we will see deeply into it. Now consider a two-phase induction machine. The reason we took for two-phase induction machine is that it is easy to understand and relate to it. Now, so we have this two-phase induction machine, and these two phases are balanced. Now let me draw this. This is my rotor. Round rotor will be there, and we have now two windings instead of one. So that we will see. This we know, main winding. You will call it as M, and there will be another winding which I was talking. I will call it A. So M being main winding and A being the auxiliary winding. Now we have two windings. Now your stator has two windings, which is A and M. Later we will be addressing these two M and A as auxiliary and main windings. So let's say now if these two coils are, I'm just trying to supply these two coils. So before that, let's see how this axis will work, because we know this. So the coil M, if you see, let's say your coil M is here, and if you use the right hand thumb rule, maybe you will get the axis of M here. M coil axis. And now if you place a similar auxiliary winding on these two slots, and now you will get a coil using the thumb rule. This is a coil axis. So this is how these two axes would look like. Now your stator has to balance two phase winding A and M now. Now you later, if these two coils are supplied with a balanced two phase currents, so then they will definitely produce RMF, because there are two forces for it, and you are flowing a two phase current which are balanced through it, then they will definitely produce a RMF. You will write the equations for it. So we have two currents. Uh, Now let I have main winding and also auxiliary winding. I'm using the subscripts for that. Now instantaneous values of these currents, the time at that uh, instant where we have given the current, alternating current, we will have Im, which is the main current flowing through, that is I max cos omega t. Now Ia, that is auxiliary current, This is Im max and this is Ia max. If you're taking Im as cos omega t, that is 0 degree, and this auxiliary is sorry, only 100 and sorry 90 degree apart, so it will be omega t plus 90. If it's a balanced three phase, it will be 120, right? So in the same way, if it's a balanced, because I told you it's a two phase balanced induction machine, so each phase would be displaced by a 90 degree. Now your Ia and Im will be like this. If I am taking Im as reference, your Ia would have a 90 degree phase difference. So till this point you understood. Okay. Now see here, let's assume that the amount of current, the maximum amplitude that we can able to flow these two windings, auxiliary and main, is same, then we will have this expression contains to this. So if we both are equal to Ix max, let's say Im max is equals to Ia max is equals to Ix, because they are same, then the both magnitudes will be same. Now tell me, there are two windings. Let me just draw here. Now we have two windings here, and this is your main winding, this is your auxiliary winding, and I'm flowing two kinds of currents through it. Both are sinusoidal. Now the RMF where we definitely produce, you have two different currents that are 90 degrees apart in space and the balance supply. Now if you're trying to see the RMF will be generated or not, it will definitely will generate. And let's say it says in this action that in this direction, and let's say it's called Fs, and the field will be rotating with the speed of Ns. These details about the speed and the rotations are also discussed in previous week, so please refer to it. Now RMF direction will be always from leading phase to lagging phase, and that's what the nature of RMF is. And the speed of the field here would be synchronous speed. So these two conditions are not so uh, new to us; they are familiar, because RMF direction will always go from lead to lag, and there are a lot of um, confusion about what is a speed, about what is a synchronous speed with respect to what is that this discussion we had. And now if you understand that, this will be very easy. Now the speed of the field here would be synchronous speed, so no matter what the supply is. So your rotor field would be different. The rotor field would be the same. Yeah, rotor speed would be different. The rotor field speed would be same as the synchronous speed. And if I'm taking this as Fs, and the direction would be from leading to lagging, that's what the direction would be, Fs. So now once this field is produced, so RMF produced, and you are now whatever windings, everything we have placed it is in the stator. So there is no information on the rotor. That no, rotor is not being intimated that whatever winding we are placing, whether it's single phase or two phase or three phase, your rotor will not be having any idea. They are unaware of it. Now But here, if you see, we have already generated a RMF irrespective of this phase, of course. But uh, this particular field which is being produced, rotor is not aware what is the kind of RMF this is. Definitely, whatever it is, single phase or second two phase, whether it gets hands on any kind of RMS, then it will definitely say, okay, if you have RMS, torque will be produced, and equation can be drawn, and equivalent circuit analysis can be done. So everything is possible if you have RMF with you. Now your motor will try to accelerate in that particular area. Uh, Torque will be produced, and like in that particular direction, because you have given a external movement and your motor is running now and it has a clockwise speed of the field now. And finally, when you see the behavior of it, once you are able to give this, your motor will start to accelerate and the efficiency will be very good. And finally, it will settle to a some rotor speed NR, you can say. And so what we can do then we can go proceed for per phase analysis and all the kinds of discussions and uh, any trials we can do around this particular machine. Okay, now since all the concepts and conditions are same here, we can also do the same kind of study which we have done for the three-phase machines, like going for power calculations and torque calculations. Everything is normal. It's just very minute differences will be there. Everything, all analysis is similar to the three-phase. So power equations, air gap equations, and the torque equations, everything will be same. So if I, for example, if I write the air gap power here, there you remember 3I2 square dash into R2 by S. That's 3 refers to the number of poles. Since all the behavior is matching here now, and this is in two-phase uh, family of these machines. This two-phase family will have different kind of rotations. The three-phase family will have three times the I square R loss, but since it's a two-phase, it will be a two times the I2 dash square multiplied by R2 dash by S. Okay. So now the two here refers to uh, uh, the number of phases here. It's a two-phase motor, so definitely it would have the two times the I2 square R2. So that's what I want to do. Now your all the different analysis will be similar from now. So since this three-phase is the supply which is generally available, and that's why these three-phase induction machines are very popular, which we discussed before. So now, if we have a two-phased balanced induction machine and we want to run it, we require a balanced two-phase supply, right? But what's more prevalent in the world is a three-phase AC supply. Now, instead of getting 2G and seeing all the issues with it, instead of making this two-phase and having issues with it, what people will do, they will make a two-phase balanced induction machine and they will go for this kind of Scott connection, which you have might have read in the transformer syllabus and all. So this transformers has a concept of Scott connection, where whenever we have a two-phase balanced in this particular supply or anything. Now we want to run it and we require a balanced two-phase supply. So we can use the Scott connection, which is very famous connection in transformer industry, and we can change this particular three-phase to a balanced to two-phase supply that that is definitely which going to convert our highly rare two-phase balance supply to into a three-phase balanced supply. Now the torque speed characteristics will also remain same for both these two, and I mean similar means similar curves, but the behavior and trends are always same. Now, in a single phase induction machine, if you see how to analyze it, so how to analyze the uh, torque speed, this all the starting methods, braking methods, everything and all, how to be familiar with it. So we'll see that, but before that, we will have to find a way how to analyze these curves. So therefore, the idea is any unbalanced two phase we will take, and current or voltage for the readings which we are sensing for the motor, and then we can show that of any two balanced systems has a balanced positive this one, and also balanced negative sequence components. So the sequence component solving is very important in the nonlinear systems, because even though uh, even though the whole supply is balanced, it is very well known technique that if you can uh, make it and make solution in terms of this particular sequence cases, and it will be converted into a three phase back using this chord connection and also some laws and all. Yeah. Now you see, solving these sequence components is what it is very important. Now we know that in a three phased unbalanced supply, whether it's a current or voltage, if it's three phase unbalanced, they can be broken down into three balanced systems. There is positive sequence components and negative sequence and zero sequence. I am writing it here. And if we have three phase unbalanced system, whether current or voltage, anything, and they can be broken down. This is unbalanced, broken down into positive sequence, negative sequence, zero sequence, and individually they are balanced. That's the beauty of it. And that's what this all the sequence analysis is all about. So you can break down a three-phase unbalanced system into a balanced sequence components having positive sequence, negative sequence, and zero sequence. Now, if a circuit is energized from any unbalanced three-phase voltage, how to find out those currents in the circuit? So you need to go for positive sequence, negative sequence, and zero sequence, and you have to find the currents and add them up and to find the resulting currents. So, like, see, you have a three phase, and now you should have to go to first step is we do the positive sequence, negative sequence, and zero sequence. So if a positive sequence is having a phase different, like phase relationship as A, B, C, and your negative should have a reverse in that particular uh, notation, and it will be A, C, B. So in the zero sequence, it means they are co-phasors. So there will be nothing a sequence of the machine, just close. So with it, you can write it as co-phasor. Okay, these are co-phasors. So now once you have the voltages right now or like this, and then you can easily find the currents. So you find the currents and then add them up individually. You find the current here, and add it everything. You will get the resultant current. Okay. Now in case of balanced, not balanced. Now if you have a unbalanced two-phase supply. Now if you have an unbalanced two-phase system, so again you have to go for sequence components, which is just a two-phase. There will not be a co-phasor element, but you have a positive sequence and negative sequence. you have the positive sequence here and you have the negative sequence here. There won't be any zero sequence since it's a two-phase unbalanced one. Now consider this particular scenario and let's analyze it for a motor having two-phase unbalanced. You have this motor and you have this auxiliary winding here, sorry, main winding here. I'm passing this M IA. So now we have M and IA, and there is no need that they both should be balanced or not. They could be unbalanced also. If we are assuming the worst case, maybe they are unbalanced. So then uh, then we have to go for this sequence kind of analysis. So I'm assuming this A and B are unbalanced. Sorry, M and A are unbalanced. So what is the definition of unbalanced? So they could be of any magnitude. They need not to be same magnitude. So there is no need that they both should be of the same magnitude. They could be a different magnitude, and the phase difference might not be 90, because a balanced two-phase system would have a 90-degree phase difference with equal magnitude. But I'm assuming this IM and IA are unbalanced, so they could be of different magnitude, and they could be of different magnitude, and the phase difference might not be equal to 90 degree or less than 90 degree. So anything could be the phase difference, not equal to exactly 90. Now these are unbalanced situation I'm considering. So then your IM, now I'm going to sequence components analysis. So since it's a two-phase, I will have negative sequence and positive sequence components. Now I am splitting these unbalanced components into positive sequence and negative sequence, which will in turn be balanced. Now I am individually unbalanced. Now I will write this IM as a phasor sum of IM1 plus IM2, where 1 is positive sequence and 2 is negative sequence. That's the notation I'm following. Now individually IM1 and IM2 would be definitely balanced. So that's the concept of sequence component analysis. Now similarly I will write for the IA, where IA is IA1 plus IA2, positive sequence component of IA1, negative sequence component of IA2, and individually they are balanced, but when add them they will be unbalanced. So now how can we apply this concept to a single phase induction machine of ours? So let's say we have a single phase induction machine where it runs on single winding. So we saw that there won't be any starting torque for the motor. That's well and good. Now that's the first observation, because there is no starting torque for the motor. It won't start unless you give an external force to it. Now therefore we have to do something about it, and then we started discussing about this concept of auxiliary. So what I will do, actually this is what we have. We started the discussion of two-phase like auxiliary due to we saw that if your motor is only having this particular kind of setup, that is single phase, there is no torque produced because of it. We discussed that the torque can't be produced because it requires two speeds, which is not possible right now. Two fields, you have only one that we saw before. Now then we introduced auxiliary winding to have two different fields so that your RMF will be induced. So we saw that by using that we will definitely can make the motor rotate. So that's why I'm assuming a condition. So this I will imagining I have a motor So I will have this main winding here. I will imagine a auxiliary winding. Your rotor is like a short circuited rotor, it's cage rotor. Now this is a main winding M. This main winding M and this auxiliary winding A, and these main winding and another winding are, I'm just assuming there is another winding. I'm not exciting it. That's the important. So this particular A, not exciting this winding with any supply. So then it's similar to my single phase induction machine. There is no supply given to it, which we don't excite it. There is no magnetic axis. So now only this main winding we will excite, and this is M, which will be exciting with the supply. So this both situations are almost similar. So I just place a coil there. There is no need of any current passing through it, like current given supply to it. It's just you need to give the supply to your main winding directly. Now when we excite this M winding, it will carry the current IM, I capital M, the current which we have drawn here. And IA, of course, definitely it will be zero because we are not giving any supply to it. It won't. It's not excited. There is the current won't exist in that winding anymore. And the voltage you have given supply, let's say it is V bar M, and current will flow here, and current won't flow here. So now we will say this is like a balanced two-phase motor, like two windings with M and A. Now M is carrying IM, and your A winding is carrying zero current IA. So this IM and IA is equal to zero are the unbalanced two-phase currents. That's what I assumed my discussion with. They could be unbalanced also, right? Now IM and IA unbalanced two-phase currents. Now we can break these two unbalanced components currents into positive sequence and negative sequence. So I think I wrote already this IM1 and IA2. I'm just quickly writing it. IM1 IA1 IA2. Okay. Now these are unbalanced, and these IM1 and IA1 are balanced two-phase positive sequence currents. And now this IM1, IM2 and IA2, these are balanced two-phase negative sequence currents. So this is unbalanced and these two are balanced and balanced, but positive sequence and negative sequence currents. Now if you see these phasors of this particular IA1, IA2, IM1 and IA2, because they're positive and negative. Now there will be a phasors. How will these IM1 and IM1, IM2 and IM1, IM2 phasors would look like? See the phase sequence of one winding, like AM winding. Say, see there are two phases now, A phase and M phase. Now they are forming a two-phase balance system with IA1 and IM1 individually, and IA2 and IM2 individually. Now if positive sequence is having one phase, as say some X phase, your negative sequence will have its reverse phase. That's what this positive and negative sequence phase. Then the third one, co-phase, will have no phase. They both are in same phase. So if IM1 and IA1, let's say, balanced and have phase sequence AM. See, you have this okay, it should not be like this. This is a phasor, this is another phasor, and this is IM1 positive sequence component. They are 90 degrees apart. This is IA1, and now it is IA1 and IM1. These are the positive sequence components. And what will be the phase sequence here? It is, I'm assuming the phase sequence is AM here in the anticlockwise direction. If you see, IA1 is leading IM1. Now your negative sequence component phase decrease will be phase sequence will be reverse. It should be MA, and your M should lead the I. So how it should be? This is, if this is IM2, the length would be same, and you will have a IA2 here. This is how it should be. Now auxiliary winding current IA2 will lag your IM2 because it should have a negative phase sequence. So from the figure of these two phasors, what I can write, some small observations, what I can do from here is IA1. So this particular IA1, if you want to write it in terms of IM, so what would you write it? So this is 90 degree. You can take the projection of this IM1 onto IA1. Like you just have to rotate it. So in complex plane, if you multiply your term with J, that is J is what, one at an angle 90. So if you multiply this IM1, it means you are giving a 90 degree rotation to it. So if you give a 90 degree rotation to IM1, it will definitely be IA1. So IA1 is nothing but J times IM1. This is 90 degree rotation. And now if you see the bottom one, IA2, it is also J times IM1. If you multiply J, it will go like this. If you multiply with minus J, it will have a minus 90. So you need a minus 90. So IA2 would be minus J IM2. So IM1 and IM2, we are writing those two in terms of IA1 and IA2. Now IA1 and IA2 are individually balanced, and individually they are balanced, yeah, positive sequence and negative sequence. IA1 and IM1 represents the yeah, sorry, yeah, I was saying this IA1 and IA2 are auxiliary windings, positive sequence and negative sequence components, and IM1 and IM2 are the main windings components. So I have converted this IM1 and IM2 in terms of IA1 and IA2. So I will just substitute these values in the previous equations I got, and we will see what we will get. And I request students to mute to avoid any disturbance or interference. Okay. So now I'm writing it here. IA1 and IA2 I have. Mr. Ajay Kumar, can you mute? So, okay. So, IA is IA1 plus IA2. IA1 is nothing but minus J IM1 plus IA2, sorry, it is plus J IM1 and minus J IM2. So minus JIM2. Now, but we know we are not exciting this auxiliary winding. I am exciting only IM. IM, there will be some current will be flowing, but through auxiliary winding there is no current. So IA is equals to 0. So if you substitute 0 here, and what you will get, IM1 is equals to IM2. And the positive sequence magnitude of main winding current and negative sequence magnitude of IM2 will be 0. So IM is equals to IM1 plus IM2, and these two are same. So what I can say, IM1 is equals to IM2 is equals to IM by 2. I can assume that this is a half of IM. So half and both are same. Then they definitely should be IM by 2. That's the magnitude of current. So I will consider one sequence at a time, and I will see how this motor operation would be. Okay, because individually in positive sequence and negative sequence we saw uh, hello. Okay, so what I'm saying is, let's consider positive sequence first, and we will see the direction of what is the direction of RMF produced there, and what is the speed produced there, and what are the directions of it, and then we will see the negative sequence separately with by reversing the phase sequence, and we will see how the direction of your RMF and direction of this speeds would be, and then they will see the resultant torque equation, and from there we will observe how exactly it is behaving, and when we club those two we will see the exact operation of a single phase induction machine. So now let me consider just my positive sequence, and I have a rotor here, so now this is a cage rotor, and let's say IM1, because it's a positive sequence, IM1 will be flowing through this main winding, and the current flowing through would be IA1. Individually there will be current IA1 and IA2, but in when you add those two they will be 0 because IA is 0. Okay, now because of these two currents IM1 and IA1, rotating magnetic field would be produced, and the direction of RMF we know it will always be from leading to lagging. So here what is lagging in this positive sequence? A is lagging and M is A is leading and M is lagging. So the direction of RMF, let's say your RMF is produced, and I'm calling it as FS1, FS1, and the direction of FS1 would be leading to lagging, A to M in this direction. So the speed of this field would be synchronous, that is NF is equals to 2F by P. That all we discussion we know. Now, because these two are individually balanced, IA1 and IM1, IA1, IM1, these are balanced two-phase currents. RMF is produced. This is FS1, and the direction would be from leading to lagging, which is from A to M. That is the clockwise direction we have got. Now, if you consider the negative sequence, you will have a rotor here, and now you are flowing IM2 to the main winding and IA2 to the auxiliary winding, and now there will be RMF produced because both are balanced, but the direction would be opposite of it, because in this negative sequence the phase sequence is MA. IM2 is leading, IA2 is lagging. Your direction would be leading to lagging. So M to A, this direction is it, but the speed is, the field speed is ns only, 2f by p. Speed is ns only, but the field you have observed is in RMF. The direction is from leading to lagging, so M to A here. Now, in the positive sequence case, in the negative sequence case, you add these two, that it will give the case of a induction, single phase induction machine with main winding alone and no auxiliary winding. So that's the case we are assuming also. So the reason we have introduced this auxiliary winding and doing it in the sequence case, positive sequence and negative sequence cases, because then they will be balanced and they will know RMF directions and all. Now you add up these two conditions, case 1 which is positive sequence, case 2 which is negative sequence. If you add these two, then it will give us the case of single phase induction machine, where there is only one winding, main winding, and auxiliary winding effect will not be seen there. That we will see in detail now. Suppose now, let's say our rotor is rotated by say some external force in clockwise direction NR. So this is the direction we are giving NR. Forcefully we are given some rotation to our rotor. Now for positive sequence, if you see, so the direction of positive sequence fs1 is clockwise, right, and the NR which I have given is clockwise, right, both are same here. Now your both RMF is clockwise and NR is clockwise, they both aid and you will have a forward field. Now for the negative sequence, if you see, the RMF produces anti-clockwise. Here you can, the top you can see the anti-clockwise field, and now NR is what you are given in the clockwise. So they both are not in the same. So they both will experience a kind of backward field. They both are not aiding to each other. Opposite. They both are opposite, and they both are the same direction. Now, if you see the torque produced, that the torque will always have the same direction of your field, that is fs1 and fs2 in their respective positions. Now, because of this forward field and backward field, the torque produced is also have the same nature of it. So let me just take some extra. Backward field. So I'm just quickly writing it, this one, and I have this one. This is positive sequence and negative sequence. I have a field like this here, fs1 this direction, ns this direction, and nr also this direction. So but in the negative sequence, fs is this direction, ns is this direction, nr is this direction, right? Now let's see the slip in the both cases. Slip we know ns minus nr by ns. That's what we know here. Now your nr is equals to ns into 1 minus s. So here the slip is s, and the field produced is forward, and the torque produced, I am naming it as forward, means F. The torque, electromagnetic torque, is also same direction of as of field fs1. Now if you see the negative sequence, your slip will be ns, but ns is in opposite direction, ns minus nr if you take clockwise as base, and ns is in opposite direction. Now if you solve this, your ns would be nr is equals to ns into 1 minus s. So here your slip would be the slip 2 minus s. So where this s is nothing but ns minus nr by ns. So this particular thing, if you rearrange it and you take negative common and ns minus nr plus nr will have like this by minus ns. So minus minus will cancel and ns minus nr plus 2 nr by ns will be like this. And okay, so the ns 2 minus s, this is s slip. Now if you simplify this, you will get 2ns minus ns, that is ns plus nr by ns, which is exactly this particular slip. So you can replace this slip as 2 minus s. So the slip in the negative sequence analysis would be 2 minus s, and the torque produced here would be TEB. I am giving it. It's a same direction as FS2, which is backward field, which is forward field. That's why these subscripts F and B. So if you want to calculate the net torque here, what is the net torque? One is in TEF and one is TEB. So you can do it TEF minus TEB. Now, what is the equivalent circuit of these two sequences? So ultimately we need to add these two, and the torque equation which will be the net torque equation would be the actual torque equation of your machine. Now let's see the combined equivalent circuit of it. Now we will write it in terms of positive sequence and negative sequence only. Anyhow, these are single individually we are seeing, and the individual equivalent circuits will also for per phase equivalent circuits we will see, and see how these equivalent circuits will be of these two sequences, for the positive sequence and negative sequences. For the positive sequence, I will have all the subscripts as 1, R1 X1, and here I will have 1 XM, now the input voltage I've been giving it as VM1, okay, and R1 X1, this is JXM, this is X2 dash, your R2 dash by S. And let's say the current flowing through in this winding is IM1 from the supply itself, and the current flowing through your rotor resistance is IF1. I am saying the forward current in the positive sequence. Now IF1 represents the forward current. Now if you see the negative sequence, we will have IB1, which is the backward current. Same equal circuit, but the currents and notations will be a bit different here. And the supply here would be VM2, R1 X1, X2 dash, R2 dash by, here the slip is not S, it is 2 minus S, right? It is JXM, and here it is IM1, and here I am flowing current of IM2, negative sequence current, and let's say the current flowing through here is IB1, it is backward current. Now if you see the current flowing through the supply, that is VM1 is flowing current of IM1, VM2 is making current flow of IM2. But what we have seen in the previous discussion, if you remember, IM is equals to IM1 plus IM2, and both magnitudes of IM1 and IM2 are equal, which is nothing but IM by 2, right? So here IM is equals to IM by 2, IM2 is equals to also IM by 2. Now you are seeing two different circuits, which is positive sequence equivalent circuit and negative sequence equivalent circuit, having same current flowing through the supply. So if two currents are having same, I can connect these two in series, right? See, IM is flowing like this, like total splitting here, and then it is joining here, and it is also having IM by 2. Now I will join these to this particular branch here, and this IM by 2 will flow here, and it will come like this, and it will again flow here, and it will again split here, and it will come back. So this particular will be outside, this one and this one. This is the total. Now you are connected these two in series. Now VM1 is in series with VM2 and IM1 is in series. So this total would be VM, which is a summation of VM1 plus VM2, right? Now if you see the net torque here, TF minus TB net torque, it's a two-phase machine. The torque and power, air gap, everything will be, equations will be same, analysis will be same. So the rotor current here is IF1 square multiplied by R2 dash by S, and in the backward it will be 2 times IB1 square multiplied by R2 dash by 2 minus S. So, and the total voltage VM is equals to VM1 plus VM2. But these are the voltages and torques of the two-phase induction machine which we are started with. So let's say this is equation A, is important equation. We have the torque equation right here. Now if you have a look at the original circuit with which we have started our discussion today, now with which we have started it, now we have combined both equations. We got the IM here, sorry, VM at the input. So we have only this circuit. I started with this main winding and current will flow IM, and this is my machine, single phase induction machine. Now in the equivalent circuit you saw, so this is the circuit and I got the VM and everything seems okay, the torque is okay and everything is okay. One thing which is not going as per the standard is the current. Now instead of IM here, in my equivalent circuit which I have brought it up this time, even though I am having VM here, I am having a current of IM by 2. So that's what we have observed. IM1 and IM2 are current in series, IM2. So now if we somehow make it IM, so let's say this is a single phase motor and this is our present case. Everything is same, VM, stator, rotor, everything is same, but this current is the one thing that is bothering us. Now if we somehow make this current IM2 as IM, then it will, everything would be okay. My equivalent circuit, the original would be VM and IM, and if I make this IM as IM by 2, then it's also VM and IM, so everything would be same. So what we can do to make this current double? Any idea how we can double this particular current? Simple. In the entire circuit, we have impedances. So see, whatever current it is having, it is because of voltage and all the impedances. So the voltage divided by all impedances is giving a current of Im by 2. So now I want to change this current twice. So to make it Im, what I will do, voltage will remain same. I will double, sorry, if I half it. If I make all the impedances half, so I just send this to this side and take it in the denominator. So if I can half all the impedances by this factor, then the current would be doubled. So from the equivalent circuit, if you see now, Vm is same, and I will divide all the impedances in this particular equivalent circuit, you see, by 2. I will make all them half. Then whatever you will get, the current would be twice. Current on would be Im. So that we will see, but we are losing on time. We only have 40 minutes for the problems. Okay, one thing we will do, we will just first solve the problems, and then we will get back to the discussion. If we have some time, I will complete this, or else we can continue this particular thread next week also. But let's solve some problems based on the starting methods, which will be important. So let's start solving some problems, and we'll get back to it once we have time after finishing these problems. Okay. So please, everyone, take pen and paper, and let's solve the problems along with me. These problems are on the starting methods only. It will be very easy if you remember those formulas like starting current in DOL, or what is a, see, the purpose of going for starting methods is only to have reduced voltage at the starting, reduced current at the starting, so that you won't see the spikes and all. So there are different methods if you remember. Direct online starting is okay, full voltage starting, and there are reduced voltage starting methods, that are reactance method, reactor method, and auto transformer method, and also star delta method. So in each case, the starting current is being reduced by some factor, some X tap ratios, and if it's a star delta, it's 1 by 3 and 1 by 3, and some other. There are many methods, and you can refer to it. So if you remember, those discussions will be very easy. Let's solve these questions now. So the first question, so there's a three-phase 440 volt line to line voltage squirrel cage induction motor is given, and it has a efficiency of 80%, and power factor is given, it's 0.8 at the full load. These are our full load efficiencies, and the starting current at the rated voltage is 4 times the full load current. So one such key information is given: starting current is equals to 4 times the full load current. Okay. Now the supply has a limitation of 1 kiloamp line current at max. Okay. This is the limit on supply. Input supply line to line current maximum is equals to 1000 ampere. Okay. What is the question now? So what should be the maximum permissible power rating of the motor if I am going for a DOL starting? See, whatever starting method we are going, there is a limit on the source. Your source cannot give whatever amount of current. Whatever might be the requirement, your source might not provide. So that's what exactly given in this circuit, in this question. So they're saying that whatever might be the load, the supply is limited for 1 kiloamp only. So maximum permissible kilowatt rating it was asking. So we will take everything at its maximum. Okay, let's say you are drawing the starting current, because at the starting only high current would surge. So my starting current, maximum possible starting current is 1000. That's what your supply limit is, right? And now at this particular starting current, let's calculate how much is the full load. So your I full load limit would be your starting current limit divided by 4 from this particular relation. Now you already know your starting current has a limit of 1000 by 4, which is equals to 250 amps. So it says that the instant where you will able to draw the maximum supply current as a starting current, at that instant you will find your full load current to be around 250 amps. Okay, now I got all full load current I know, full load efficiency I know, full load power factor I know, everything I know. So what I need to calculate, maximum permissible kilowatt rating, that is shaft power, that is output power, how much it is we need to calculate. So you can't calculate the output power directly from the given questions, because nameplate details nothing is given, but you know the input line to line voltage and power factor and efficiency. So if you know how you can calculate output, if you know efficiency, this input multiplied by efficiency of full load. Now the input formula is root 3 VL IL cos phi and efficiency. So this is maximum possible limit. So all are at maximum. Input should be maximum, and the IL should be maximum line to line limit. Full load current it is. Now root 3 times. Here your VL line to line is 440. That's in the question. And your IL limit, you got the IL limit as 250 full load current. And power factor at full load is 0.8 multiplied by the efficiency is 80%. Again a 0.8 factor. Now please tell me the answer. How much is it? 121.932. Okay, let me also calculate. 0.732 multiplied by 440 250. Yeah, 121.932 exactly. Good. So if you are going for a DOL starting method, so your maximum permissible motor rating could only 121. So that's the maximum limit you can go, because you can't go beyond it. Your motor can't give more than that. Is whatever. Even if you go for bigger motors, you are not capable to utilize that completely, because your starting current is such that your starting your full load current is limited to 250 only. So that's not a very good sign, because you can't go for higher rating motors. Now that's it. That's a simple question we are solving here. So if it's like that, if you're going for dual starting, so what is the maximum permissible? So maximum permissible kilowatt rating of your motor is POP, output power max is 121 kilowatt. So now estimate the maximum permissible power rating of the motor if auto transformer starter is used and the tap ratio is 75% of the voltage. Now it's again easy. The X is the tap ratio. Now whenever you are going for a tapping, you know you are limiting your full load current. Now whatever your new full load current would be this times of this tapping ratio times the full load current. Now see, IFL new is equals to IFL multiplied by 0.57 square. You remember that x square times of current. So please go through the formulas and discussion once again. So you will remember that if you going for x times ratio, your current will be reduced x square times. Here the tap ratio is 75%. Now you know the new full load current, and you can calculate the uh, 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 output rating again. But however, your starting current limit of the machine is 1000 amps. That's it. For this particular starting current, you need to calculate the new IFL. So how much is it? IFL is equals to IST line by 4. That's the equation. Now this IFL is equals to IFL times 0.75 square. IST line limit divided by 4. So it is 1000 divided by 4 multiplied by 0.75 square. So this is your IFL, full load current that motor can draw if you are going for a auto transformer starting. What is your new full load current limit? 1000 by 0.75 square. 0.75. 2.25. 1000 by 2.25. It's 440. So you can have a more full load current in. You can utilize more full load current limit in this auto transformer starting. Now let's calculate the output power. Same. So input power multiplied by efficiency. Now you will have the input power same, root 3 VL IL cos phi and efficiency. Root 3 times 440. Your new limit is 444.4 and efficiency power factor is 0.8 and efficiency is 0.8. So how much is this? Please calculate once. 444.4 multiplied by 0.8 multiplied by 0.8. So I got 260. Is it? How much? .216. Okay. .74 kilowatt. So that's the maximum permissible rating of your machine if you are going for auto transformer starting. Now if it's a star delta, it's same thing, but if in a star delta the factor would be your full load limit would be 1 by 3 times the full load current. So your FL new would be IFL divided by 3. This is the IFL in the DOL. So which is there is no starting method. Now if we go for it, IFL by 3 is equals to starting current limit by 4. Now this IFL is equals to 3 times 1000 by 4. 750 amps. Now again calculate the output. Multiplied by 440, 750, 0.8, 0.8. So 365.879 kilowatt. This would be your maximum permissible kilowatt rating if you are going for a auto transformer starting. So this is that's what you have to, the takeaway from these all this is the motor ratings are improved with the starting methods itself. You can see you can go for a bigger motors, and you can design your motors for a bigger ratings, and you can utilize it even though you have a limit on the maximum supply current. And because of that starting methods only, we have seen how the factors of input voltages to the machines will go down even though the supply remains same. If you place a auto transformer or star delta in between, we can see how they will reduce the input voltage altogether that is going to the machine, and you can improve the output permissible kilowatt rating. But we also saw that after in the last week discussion how this variable voltage and variable frequency power electronic drives, they are going to replace this starting methods because they are also providing a smooth reduced voltage starting that we already saw. Anyway, coming back to the problem here. So this is a different question with all the different um, data. We were given a 16 kilowatt 440 volt line to line 3-phase squirrel cage induction motor. It is having a full load efficiency of 85%. Now full load efficiency is 85%, and power factor full load is equals to 0.8, and the full load current is equals to 25% of the starting current. Full load current is equals to 0.25 of starting current. Okay, this is one relation we were given, and the full load torque is equals to 64% of the starting torque. This is another one. So to reduce the starting current, yeah, definitely, auto transformer starting is used with the tap setting such that we get full load torque at the starting. Okay. Previously, when there is no any starting method, you are getting starting torque, which is at the starting you are getting some 0.64 times over TFL divided by 0.64. Now they have set a auto transformer starting, that means they have used some X, that is the tap setting in percentage. So they have put some X. So let's say this is a torque speed T, and this is speed. So this is the starting torque. So if there is no starting method, you are getting some starting torque. Okay. Now TFL, when there is no starting torque, your full load torque is 64% of the starting. Nice. Now whenever you are having auto transformer starting, your full load torque, you are getting that full load torque at the starting itself. So TEFL is equals to TE starting in the auto transformer. That's what you get. And another purpose of using this also reducing the starting current. So your starting current goes down, and your torque will also be full load torque will also is getting improved. Right. Now you just have to find the tap ratio here. It's simple because if you see the relation in the torques, how they are going to improve. Now the starting torque in auto transformer is equals to starting torque in DOL multiplied by X square. So this you remember, right? Now X is here the tap ratio, of course. Now you see this starting torque in auto transformer and DOL. We know the relation between these two, right? You see the torque relation here. This is in the DOL and this is in the auto transformer. So in the auto transformer, your starting torque is equals to nothing but the full load torque. But in the DOL, your starting torque is TEFL upon 64%. That is full load torque divided by 0.64 multiplied by x square. So these two get cancelled, and from here you can find the x square. X square is equals to 0.64. Now your tap ratio is 0.8. So it was asked in percentage. It is nothing but 80%. So in between supply and there is your machine, and you will have an auto transformer here, and the supply is this one, and you will get a three phase. And if you set it at 80% tap ratio, you will have this machine's torque characteristics and also the starting current will be different. So that's how you can find the tap setting in percentage. It's just a simple relation only. We solved all these formulas, the torque relations and current relations. I would request everyone to go back to our starting methods discussion week and refer to the notes and PPTs and recordings. You can easily understand how we got these relations and how your starting torque is getting reduced in the different starting methods compared to the direct online starting. Now the line current drawn by the motor at the starting is how much? So at the starting, if we want to see how much starting current is being reduced, because in DOL you will have some X amperes, but if you are using some auto transformer or something, you will have to go for improved or reduced starting methods. I mean, whenever you're going for any other starting method, it means that you are reducing the starting current burden. Now that reduction we will see. So by the end of this question, we can see visually so how much is direct online starting line current at the starting, and what is the auto transformer starting current, and how much we have reduced. So the question asked is, what is the starting current drawn by the motor line to line in auto transformer? So much. Now in auto transformer we know, say first we will see the starting current by the motor in DOL. V rated divided by ZSC. We remember this formula. Now your IST motor in auto transformer would be X times your I starting motor in DOL. X is nothing but the tapping ratio. Okay. Now we need to find this line current, and we already know this X in the last problem. It is 80%, 0.8. Now another relation which was given in the formula is, if in the question is starting current relation. Now in the question it was given your full load current would be 25% of the starting current. So that's one relation which was given without any starting method. Now if you calculate with this relation whatever the full load current you would get, and you will just calculate the auto transformer starting current then easily. Now you are starting, let's calculate from your without any starting method. Let's say in DOL, you know, I starting DOL machine is equals to IFL divided by 25%. So this is the same thing. I have this one. Yeah. So we got I starting torque is equals to full load current divided by 25. So this one, full load current divided by 25. Oh god. One second. Just need to. Okay. Now we know this relation which is already given in the data. Now let's calculate the full load current first. Then we will go for starting current by substituting here. So from the nameplate details, if you see, it was given it's a 16 kilowatt motor with a efficiency of 85% and power factor of 0.8. Now I will use that information. I know P input multiplied by efficiency is P output, which is 16 kilowatt motor, and efficiency is given. And input I can calculate root 3 VLIL cos pi, right? Now let me calculate here root 3. What is the line voltage? It's 440. IL is full load current which I am interested in. Cos phi is the power factor. What is the power factor? It's 0.8 is equals to my okay, this is input. If I multiply this with efficiency 0.8, that is my nameplate details. Name shaft power, that is output power 16 kilowatt. Now from this I can easily calculate the full load current to the DOL, right? 16 into 10 cube divided by root 3 into 440 into 0.8 multiplied by 0.8. How much is this? 1.732 multiplied by 440 multiplied by 0.8 multiplied by 0.8, 487.73. So I am getting the full load current is equals to 32.8. What is this 0.8 and 0.85? Okay, efficiency is 0.85. So 85. So I'm getting now 30.87. IFL is equals to 30.87 amperes. Okay. Now let's calculate the starting current that is in DOL, that is divided by 0.25. IST DOL is equals to IFL 0.25, 30.87 divided by 0.25. So 30.87 divided by 0.25, it will be 123.48 amps. Now you know the starting current in the DOL. You also know the relation of starting current in the auto transformer is equals to X times the IST, that is in DOL. So you know the IST in DOL is 123 and you also know the tap ratio is 80%. So 0.8 multiplied by 123.48 amps. So how much is that? It's 98.878 amps. Now you see, by using an auto transformer starting method, you are able to reduce the starting current burden by 123.48, and using that particular tap ratio, you can also improve the full load torque limit, same as the starting torque. And one more thing which we have observed is you can improve the power rating of the machine. So all these advantages, but of course reduced voltage you are to give to the motor. That's anyway that's there. You are having a reduced starting current, and that's the different uh, effect of this auto transformer starting. Okay, so these are some key concepts which will be very useful in understanding the starting methods of induction machine. So this all the problems which we solve today are based on the starting methods only. They will be useful for you to solve your assignments and understand the concepts on starting methods. Just go through the basic formulas which we discussed 2 weeks before. They're very straightforward. DOL, auto transformer, star delta, and also reactor. There is a factor, and based on that factor, your all starting torques and starting currents will be altered. And if you remember those formulas, it will be very easy. And getting back to input with when we don't have the output and efficiency that we have saw. Output is nothing but efficiency multiplied by input power. From that, you can calculate the currents and everything you need, even output power also. And so, yeah, if you have any doubt in this problems, you can ask. You can ask. We can discuss more. And now we can get back to the discussion of this starting methods. But it's in detail way I want to discuss after. See, the purpose of today's discussion is to understand the operation of induction machine in single phase. So when we saw at the starting, we didn't got the operation of induction machine as starting torque, because there is no starting torque in single phase induction motor when there is only one winding. So then we assumed there will be two windings and they will be produced two fields, and we went into this sequence components. But I have not completed the discussion.
Sir,
Yes, hello.
the last question,
Mhm.
he just the line current run by the motor,
Okay.
and I think this is the current from the auto transformer that X into I.
Auto transformer is X times the all are line currents only. This is line.
That is X square, no? Line current is.
This is line to line, and full load. If it is L, this is line to line here. This is line to line. This is line to line.
It will be X square or it will be X.
Is it X square? Wait, let me just check. Okay. And auto transformer starting IST line equals to
This is the
X.
current from the auto transformer. Now further auto transformer will be drawing X times the line current of that.
IST line supply. IST line DOL. Hmm. The question is the line current drawn by the motor at the starting. Okay. IST line machine, it was asking. IST line machine would be root 3
Two part
times.
this question. Suppose if it asking the current drawn from the auto transformer to the motor, another is the current drawn from the line to the auto transformer.
See, if it's a machine line current, it's x times only. If it's supply current, then it's x square times.
Yeah. So it is actually asking line current. That means supply side.
No, no,
If it is asking the current from the auto transformer.
no. Uh, See, I'll just show you. This is like this. Okay, this is the auto transformer I have, and here I have my motor, and I have this tapping going through this one, and this will go to this one. Okay, okay. This is this particular thing is IST line supply. Okay, now this particular current, whatever it is having, this is IST line machine. Now whatever this it is, IST line winding. Okay, now whatever it was asked, it is drawn by the motor. So this one, this IST line drawn by the motor is what it is asked in the question. Okay, now if you go from this, starting current drawn by winding of this auto transformer is x times the V rated by ZSC. Now we are going from back. So here it is. This is V rated, that is coming after x times V rated divided by this entire impedance ZSC, whatever you calculate. Now I starting line current drawn by the motor, which is this one. This will be again root 3 times this entire factor, because it's a delta and it will be line will be root 3 times of this this one, x times V rated by ZSC. So your supply IST line drawn by the motor is root 3 times x V rated by ZSC. Okay, now this is what asked. If it is supply, it will be x square times. Now root 3 times V rated by ZSC is what? It is IST line drawn by DOL. You got that?
Yeah, yeah, sir. I thought the line current means always a supply current.
No. Every factor will have its line component. Line supply, line machine, like that. This is the important one. Is it by the drawn by
Can
the
we say that it is the current from the auto transformer?
current? I didn't understand. What is that? Current. See, current.
Current drawn from the auto transformer.
Current drawn by the auto, like current drawn by the auto transformer. That could mean the supply current, because after supply there is immediately your auto transformer. So first the current, whatever is supplied by the supply, it will go to the auto transformer windings, and then part of it will go to the motor.
Okay, okay.
Okay. Okay, great. So what I was saying is, the starting methods, you just go through the derivation. I think this particular derivation we did it in that discussion. Difference between the machine current drawn and the supply current drawn. You pointed out it correctly. If it is supply, it would definitely be x square term times. But it is machine, it's x times only. Anyway, getting back to our single phase induction machine, I want to close the discussion even more with even more clarity. So how exactly it is behaving as an induction single phase induction machine. So the takeaway points would be, in the single phase induction machine, uh, there won't be starting torque. Starting torque is zero, but running torque would be there. So what I want to convey from this today's discussion is, we just now arrived at the equations of single phase induction motor, and this is what we have, right? This combined induction equivalent. Next week we will just complete this discussion, we will have one complete equivalent circuit with the VM and IM current, and we will have some resistance components and all, and then we will see the torque, final torque equation, and then we will substitute the conditions of starting and running, and we will see how starting current will always be zero, so starting torque will always come as zero, and running torque will not be equal to zero. So then we can justify this particular equivalent circuit is behaving exactly as a single phase induction machine, because that's what we observed. In a single phase induction machine there won't be any starting torque, it won't rotate. We have to give externally, and once we rotate it externally by any prime mover, it will pick up the speed, and during running condition you will have some non-zero torque. So that we will see even more clearly next week. We will have a good discussion, and now the time is not there, it's already 8 o'clock. Okay, so if you have any doubts in today's discussion, either on starting methods or on single phase induction machine concepts, you just you can ask now. We start with the basic single phase winding and how the flux is generated, and why torque starting torque is zero, because for starting torque you need two components with enough phase difference, and that's not happening in this single phase winding. The stator field rotor field are in the same direction. That's why it's not happening. And we introduced an auxiliary winding without exciting it, and we saw the uh, generation of RMF in this both cases. And then by combining it, we will get a combined equivalent circuit, and then we will have a one single equivalent circuit and torque equations that we will complete next week. So then we solve some problems on starting methods and the direct formula based, but concept, of course, you need to have this concept in mind. This is very important and straightforward, so don't make any mistake in this. What is asked, supply or motor or winding, everything needs to be crystal clear in your mind, and that will help you solve the problems easily. Okay, so if you don't have any questions, thank you all for joining, and thank you for discussing and participating in discussion. Thanks, Dinesh, and thank you. We'll meet next week.